bringing calculus into physics isn't quite as difficult as it sounds. We're going to start by looking at some mechanics, which is probably where the calculus is a little bit more familiar to you. We already know, for instance, that acceleration is change in velocity over time. Well, rather than looking at that over an average period, if we look at it more of an instantaneous, tiny change in velocity at a specific point in time, we get dv by dt. Acceleration is rate of change of velocity. Rate of change of means change in velocity with time, or with respect to time. So this is the equivalent of dy by dx, which is y changing with x, except we're just changing the y's and x's round. It tends to be the hardest thing people find to come across in physics the first time, is just not using y and x anymore. Similarly, in mechanics, we also know that velocity is change in distance over time. So change in displacement s over time, which means that velocity is ds by dt. You can call the s whatever you want. That could be dx by dt, dl by dt, dd by dt, but velocity is rate of change of distance with time. Okay, so let's just look at little examples of how we can use this a bit more practically. Imagine that we've got an equation. Let's just take one of our equations of constant acceleration. V equals v naught plus at, or v equals u plus at if you prefer. Let's actually have some values in this. So let's say that we had an initial velocity of 10 and an acceleration of 1.2. So for our particular object, we now have an equation that gives us its velocity at any given time. If I put a value for t in there, I'll get a velocity at that time. Let's just look what happens if we work certain things out from a calculus point of view. So let's say I want the acceleration. Acceleration, as we know, is dv by dt, rate of change of velocity with time. So if we just do that for the equation on the left, dv by dt equals, right, differentiating a constant v naught gives us 0. Differentiating an at is like differentiating, 3x. You're left with the 3. So we're just left with the a. So that's no great surprise. We already knew that a equaled dv by dt, but it is nice to have it proven to us. But for a more useful context, for an actual object given on the right, let's do the same thing. dv by dt, the 10 disappears, differentiate 10 with respect to time and it's 0. Differentiate 1.2t with respect to time and we're left with the 1.2. So this is obviously telling us that the acceleration is 1.2, which is not surprising because that's what we set it up as in the beginning. Okay, let's go the other way now. If we want to say find displacement. Now, we know that ds by dt gives us velocity. So if I just do a little rejigging of this and rewrite this. Yes, I know this is a little bit cheeky and mathematicians do this and even they admit to it being a little bit cheeky. But if we do that and then integrate both sides, then this gives us displacement. So what that tells us is if we integrate an equation for velocity with respect to time, we should get an equation for displacement. So let's do that. Again, let's do it just on the left-hand side first. So if I differentiate v with respect to time, I am integrating, v naught plus at with respect to time. So again, integrate both of those terms. We get a v naught t. We get at squared. Don't forget we have to divide by that power, so we get a half. We also get a constant, which is something I'm going to worry about in a different video. So this tells us then that s equals vt plus a half at squared plus c. You might already have figured out what the constant is, but not something I'm going to worry about. This part of the equation should look familiar to you. If you prefer, you could think of this as s equals ut plus a half at squared, which is just the equation for motion for displacement. All right, let's apply the same thing to the other side. S is the integral of our specific equation now, v dt. So S would be the integral of 10 plus 1.2t, all with respect to time. So we do exactly the same thing here. 10t plus 1.2t squared not forgetting to divide by the power, plus a constant. So again, now what I've got is this, which is an equation that would give me the distance of our object, which was originally described by that equation at the top. So now I've got an equation for velocity. I've got effectively an equation for acceleration, but the acceleration is constant, so it isn't dependent on time. It's just a equals 1.2. And I've got an equation for the displacement. So if I was given an equation for velocity, for example, from that information, I could take the equation, integrate it, and find out what the displacement would be at any given time, despite the fact that the information I was given initially was about velocity. Now, you can do this with a number of other, countless other bits in physics. I'm literally just going to pick a couple at random that aren't mechanics necessarily related. So power, for instance, very generally could be any kind of power. We know as energy divided by time, or probably more commonly, you'll see it written as work over time. But it's work because it's energy transferred. So if it's energy, really we want a little delta in front of it. But instantaneously, what power really is this. Power is dE by dt, rate of change of energy transfer. Another one that we're aware of is force is change in momentum. PB momentum this time, not power, over time. And sometimes we do even write the delta t on the bottom here. So this is exactly the same thing. Force is dP by dt, rate of change of momentum. That's just Newton's second law. But here it is written in the form of calculus instead. Just another little thing that we can sometimes do. We know, for example, that work is force times distance. But if we want to know what small amount of work happens over a small distance, we could have something like that. And we could integrate it, or we can rearrange it, which tells us this, that force is not rate of change of work done. That will be slightly different. If you think rate of change of work done is dW by dt, we already know that is power. But force would be rate of change of work done with distance. So again, it does have lots of uses, and it's something you can just play with just by looking at the simple algebraic equations and considering what their calculus counterparts would be. It's not always as straightforward as what we've just done there in that last one. We know we can do that, for example, if we had a constant force. But it does give us a starting point for more complicated instances where, for example, force could also be a function of distance or a function of time when we start to get into much more complicated equations. All we're trying to do with this is just open the door so that you can see how it might be used.